And this one is like another is like we can take the just the checkpoint because like with just we still have supervised loss, and that's give us a good indication like which checkpoint would be good. And then we find we can decide from the just training choose the best based on the like a validation side, choose the best checkpoint and fine tune it with further supervised loss. It does the best. And if we look at the analysis on BE, the German and the Italian, IT, and the Polish PL, this outperforms all the existing models very competitive on other languages. So instead, this was saying like it's a good training strategy there. Next one. Yeah, this is just like what try to break down on the errors and per language and to more clearly illustrate the one's answer is pretty consistent across different languages. Next one. And another is like because we have this kind of weighting factor into how much unsupervised you want to put into the picture, and we conducted some study. This parameter, hyperparameter beta does. I mean, the just training does kind of be sensitive to the beta, but it's not very like. I mean, it's we need to find the sweet point, but around the sweet point, it's not like you need to be very careful. Like if it's like change a little bit, is the quality changes a lot. Actually, it's pretty robust once you find the sweet point around the sweeping. And we run a few different values from the table. You can see that there are like whatever changes, but generally it's pretty good compared to like a two-stage like a pre-training plus fine-tuning approach there. And next one. And another thing actually we look at is like we compare the two different attention because like we are using conformer, which is based on transformer. There is like a attention module in the model setup. So we compared a local attention, global attention for the model. And from this plot, we can see like the global attention approach is definitely better across different language. So that's one data point. Like when you like try to explore using the conformer or transformer based approach, and some kind of application study we found will be useful here. And next one. And because we are using like a web-to-vec, there is the code book. And initially, like in the rendered XSLR, like the web-to-vec fine-tuning, that usually doesn't fine-tune the code book. But in the just fine-tuning, because we have the unsupervised loss there, so the unsupervised loss on the like just the training part, it's got updated together with supervised loss, which affects the code book. So we wanted to see like whether the code books is the reason this kind of joint training is the better. Actually, I mean, from our application study, if we fix the codebook during just training, the result is pretty close to we update the codebook. So this implies like during just training, we can like fix the codebook. So basically, we can just rely on the codebook, learned before the pre-training part. But this depends like whether you start from pre-training model or not. Another is like even with just you can learn like a reasonable good codebook compared to two-stage training there. And next one. Yeah, this is similar. So basically, like if you try to adjust this kind of unsupervised versus supervised loss, they can learn different code books, but through the just training, actually, it doesn't affect that much for the downstream performance. And next one. I think another data point in terms of we are looking at the joint training is like because for the self-supervised training there isn't a direct matrix connected to your downstream tasks, so it's hard to decide which point to be chosen during the pre-training part for your downstream task. And in this experiment, this application study, what we did is like we tried to choose different pre-training checkpoints and use it on the downstream fine-tuning. We do see like there is like a fluctuation, up and downs in terms of quality. So basically, that was saying if you do the two-stage training, there is still you need some effort to tune a proper checkpoint. But with Just, the good thing is because it has a supervised loss there, so you can just keep track of the supervised loss on your task. And to decide, to avoid this kind of decision on which checkpoint to pick for your downstream task tuning before you know any quality there, and the quality before the fine tuning. Yeah. Cool. Next one, I think this one is a recent work from our group. We further extend the Just to with Hydra, just the Hydra. So the motivation comes from this there is a paper trying to do this kind of layer-wise analysis, and they found in the whip-to-vac models, the last 3 layer in the whip-to-vac pre-trained model is more specialized to reconstruct master input. Because the self-supervised pre-training is to the contrast law to reconstruct, and that means the last 3 layers may not be good for your downstream discriminated task. So based on that motivation, what we just modified our architecture is we put the last 3 layer. We use version to duplicate our last 3 layer. One for the whip-to-vac bird loss, the unsupervised loss. Another is it's the same structure but different parameters for the supervised loss, the RNT loss. And from one of our production setups, the voice search and IME task, you can see if you compare to Just versus Just Hydra, there is a clear benefit of separate the last 3 layer parameters for supervised and unsupervised loss there. So given that, that's most of the content of this section. Next one. Here, just a quickly conclusion. Basically, is we look at the 2 problems. First, how do you scale up the language coverage for the large models? And we found that you need large model capacity if you want to maintain the quality across different language. And another way to address it to give a fixed budget is you can try to benefit from the transfer learning from reuse in previous models, the lifelong learning approach. And another is to address this kind of distracted forgetting across multiple stages of training. We can combine the unsupervised and supervised loss together to ensure you always have this kind of unsupervised component, even when you update data, fine tuning on your downstream tasks, to make sure the model doesn't forget what it learned before the self-supervised approach. And from the previous multilingual liberal speech, we found if we do just plus fine tuning, that's the best. But in practice, we don't always want to keep the large amount of unsupervised data around for your downstream task. So actually, a more recommended recipe, or also internal external when published paper is we still keep the self-supervised pre-training approach, but that is the first study which trained on large diverse audio only data. And those data is just to try to learn speech reprocessing, to try to reconstruct speech. And then on your downstream tasks, you want do fine tuning, we do the just based training. Basically, we try to make sure the model doesn't forget what it learned from the self-supervised. Instead of replace the self-supervised approach, but we do the just as the second, replace the fine tuning only approach using just. And the last layer is once you do the just, you want to further increase the number of language coverage of the model. Try to incrementally learning the model. Basically, reuse the existing model trained maybe on the small scale, and then small scale of data or small scale of language, and then try to progressively increase the language diversity, domain diversity to more domains, more language, and to avoid increase the capacity too much. But I think on another direction, as we discussed just now, we definitely want to explore to pushing the model capacity to be large. When do we really need to do that? And at what kind of stage? The model is is already really full capacity, and we need to push it. But before that, I think there are space we can push the quality without increasing the model capacity. And I think in this section, we expand the language and we expand the kind of joint training. And in next section, you talk, we'll discover that can we bring more modality, like especially on the text side, can we bring more text training into this kind of big SSL, like this kind of self-supervised approach training. And before that, I think I think I take almost 45 minutes, 35 minutes. Okay, yeah. But we can have some questions here, and if there are questions before we move to, if we have time, we'll take a break. Otherwise, we can move to the next one.
Hi, Bo. I have a question. Yeah,
sure,
that's very impressive for this work for multilingual speech recognition. Just wondering, we have in practical, we have problem of code switch. Especially, it's very important in Singapore. We have multiracial culture, and everyone talk in more than one languages. So
exactly.
Code switch is a very important problem. I just wondering, just now you mentioned just what helps the low resource language speech recognition. I just wondering, you have any insight for code switch speech recognition?
Yeah, thanks for the question. That's definitely very for us, one of the at present there are some motivation that we look at multilingual, massive multilingual. I didn't mention about the code switching because it doesn't cover any result there. But that's actually one of the biggest motivation for us to also look at the multilingual for the code switching. I think yes, as you said, like in Singapore, that is a lot of code switching. Also, like in Europe, there's also a lot of code switching there. In terms of like production requirements, that's a huge need there. And from our research experiment, we found is like, for example, if you do multilingual, it itself is already a better starting point for this kind of code switching, because like you already see a lot of data and the variation, and it's more robust compared to a single like a monolingual model there. And another thing is like in terms of just we do have some investigation in our group, like we can like bring unsupervised like code switch data to try to make the model like using just the training to fine tuning your model to make it more generalizable to this kind of acoustic difference for the code switching, because therefore people like do code switch often. Usually, the acoustic variation is also slightly different from those kind of like monoline speakers, and that can bring that aspect into it. And we do see some like in terms of what our quality. Actually, we were like internally we are also in the same data set. I think that's like created from the Singapore, so there's like Mandarin and English code switching data, and we do see some benefits. Like if we only bring like the same training data without a transcript into the picture through just the training, we do see some benefits on the testing the code switching. And another aspect actually, I think is from the text side, because the code switching, another is like the language usage, how you change it to which word is more often be changed to a different language. So injecting this kind of code switching text into this kind of like multilingual model training is also useful. I think that part, Yu is going to talk about that. So basically, what he discussed in the next session. Well, we also like had some experiment with Joyce, which is we will talk about detail, and we see benefits there too.
Thank you.
Thanks.
Paul?
Yeah.
Now, so since we are talking about multilinguality, so an unfair question would be, different languages, of course, share quite a bit of similar acoustic phonetics properties. But how about text in terms of language model? Is that a viable approach to pre-train a very large language model for, multilingual problems, and then go from there to specific languages?
Yeah, that's another good point. It's like I think thanks for the question. Yeah, so basically, in terms of multilingual, besides the acoustic, I think like usually I would take the opinion like language part is more complex than acoustic because like from previous like multilingual study like the number like we have IPA, so basically like the number of the acoustic realization the human can make that's limited. But the language in terms of text, the language used is much more complex than the acoustic part. But that's debatable. But to me, actually, one data point we have on our side is like we have been combined this like a massive multilingual ASR, the end-to-end ASR, with large language model trained on large amount of like multilingual text, and that can further boost the quality, but actually by a pretty large margin. So basically, like even your train this engine, because the engine itself has a decoder. It's a relatively weak language model, but it does capture some language model perspective. And we can see like on top of this engine, multilingual ASR models, if we bring this kind of large language model trained on multilingual text, that can even further improve the quality. So basically, this engine training here, I think a major part is because the parallel data we train for our multilingual ASR is, the amount of data is still limited compared to the large amount of text there. So that limits the capability of the decoder in our multilingual ASR capability on modern language. That's why it's like if we bring additional language model into the picture, that will bring our actual benefits there.
Thank you.
Thanks. Okay, I think we are like a pretty. Maybe we'll directly go to the next section here.
Okay, I'll try if I can share the screen. If not, maybe I still need Daniel's help. Daniel, if you're still here, maybe you can do that because it requires me restart my laptop.
Sure. Can you give me a second?
Yeah.
Let me download it. Yeah.
Yeah, the reason is both of us we have to use Zoom in a personal laptop, which we were not very often to use. Yeah, we have internal to write Google for meetings, and those software are not allowed to install on cloud machines.
Okay, let me see if I can present. Let me see. You don't see it yet, right?
No, yeah.
Okay, let me see. You see it?
Oh yeah. Okay.
Okay. Cool.
Yeah. Okay. I'll just get started. So to continue with Bo's discussion, we also want to look at how can we adding more modality to the pre-trained speech encoder. So we call it a text injection. Next slide. So this talk is based on 3 work. One is the AmSlam, and the other is Metro. And at the end, we also talk about Joyce. Next. So the goal here is we want to build a pre-trained encoder that can encode both speech and text for many language, and we hope it can learn joint representations. So the pre-train allow us to leverage large amount of unlabeled speech and text. So what if we bring it together? That is similar motivation like multilingual. So multilingual, you share representation and data across language, and you want it to improve the performance for low resource language. And for modality, it's just do the same, but it's cross modalities. So why we believe now is a good time to, let's say, there's many ways to do multimodality. So why we believe now is a good time to try a multi-modality model for encoder. So the first and the most important things in my mind is we do see a convergence in neural network architectures, especially for different modalities. So for example, if you look at nowadays, the difference between a speech recognizer and a machine translation system is actually very, very close. Like both use transformer-like architecture. And next few slides, I'll talk about pre-training framework, and it also become very similar. And also like pre-training on label data, seeing a similar convergence, like both modality like BERT and recent speech pre-training method all use mask language model strategies, which also makes it easier to learn a drawing representation. Next slide. So just like a little bit more detail for the motivation. So why we do believe speech and text can help each other. Not this is kind of orthogonal for language model. You can always shift the domains. This is from the point of a language for middle resource language. The availability of speech data can be a bottleneck. So there is a lot of speech, but they're gonna have far more text. And this applies same for label and non-label data. So it would be nice if we can leverage text data for speech understanding tasks. And on the other hand, for some very low resource language, the situation might be changed. Like you might don't have a lot written script for those super low resource language, but you might able to find a lot more videos on the website. And you hope we also hope like for those tasks, speech might be also help the text task. So ideally, we want this technology can help each other. This is a standard pre-train encoder framework for text. It's called BERT. The basic idea is to mask the tokens and reconstruct the token. Next. And we do find that for speech, we can apply a very similar framework, and which is like we first describe the feature, and then on top of those described feature, we apply the similar mask language model laws, and it can get like a very good performance on public benchmark. I didn't list here, but recently we have a paper early this year. It find like you even don't need to learn the discretized representation. You can simply just do a random projection. Let's say you random project a continuous feature to a codebook, and we still can get state-of-the-art result on many published benchmark. So this makes the speech pre-training and text pre-training almost identical. Like conformer is very similar to transformer, and both use mask language model laws. The only difference is quantize the feature and get the discretized target. Next slide. And for pair data, one popular thing in text side is it's called like a TLM. That's basically you concatenate the pair data for machine translation, and you mask it and reconstruct it. It's also get a pretty good performance. Next slide. And for speech and text pair, you can do similar things. You concatenate the feature and reconstruct both speech and text. And another way to always have small amount of supervised data. So one way is using CTC. We just like map the speech to text directly. And we also tried the TLM loss. Basically, we concatenate speech and text and reconstruct it. Next slide. So the task we target here, basically including, because now like this model can accept both speech and text. So it will be interesting to not just look at the ASR. We also interested like what about a speech to X task? Like, so for example, for multilingual speech understanding, we looking at the performance on speech translation, speech classification, and speech recognition. And we also curious about what is the performance on multilingual text understanding, for example, translation and classification. And we will always compare to a speech only baseline. Next slide. So for the multilingual speech translation, we do we benchmark on CoVoS 2. That is CoVoS 2 many to English speech translation task. That's basically you have many different language of speech, and you translate to English text. So there are 21 source language. The amount of the paired data is actually quite small compared to machine translation. So for example, this is some some example. And for fine tuning, we use we added another 6-layer transformer decoder. So compared to the size of the decoder size is quite small. So this can tell us how powerful of those pre-trained encoder. We just simply mix all the language together. There's no tricks for how to upweight the low resource or how to sample those language. Next slide. We use this XLSR from Facebook. That's basically as a baseline. So they basically pre-train a large, a 2 billion parameter large encoder on many public speech data set. And for the decoder, they also pre-train it on the text, and then they fine-tune both this encoder and decoder model. So our pre-trained data is a subset of this set because some of the data we are not allowed to use. You can see, so first we look at a smaller model, so we can ignore this larger one. We will have result for this 2B benchmark in the later slides. So you can see if we just throw in all those data and we fine-tune this joint training encoder and fine-tune the speech-only encoder, the performance is almost the same, slightly better by 0.2 blue, which is almost in the noise ratio. Next slide. So however, one big advantage of this joint pre-trained encoder is now you can easily use empty data in this framework, because now your encoder can take both speech and text modality. So during fine-tuning, so this is actually one disadvantage of an end-to-end model. So if you train an end-to-end speech translation model, you can only use the paired data. It's hard to use a large amount of paired text data. So by doing this speech plus text pre-training, we actually can easily adding empty data to this joint framework. So basically during fine-tuning, if it's speech data, then it's fine-tune both encoder and decoder. If it's empty data, the encoder is shared, so you just throw in the text and you still can train the encoder and text and decoder part. Compared to speech-only model, you can also do that, but you have to separately pre-train the decoder and the encoder. Next slide. We can see after adding those paired empty data, this 600 million parameter model actually perform a lot better. And for speech only, there's a 0.6 blue improvement. However, for this joint pre-trained encoder, there's more than 2 blue improvement, which is significant. That means with this pre-trained encoder, we can easily utilize text information for the speech translation task. Next slide. And if we further scale up this model, because now you throw in more data, and more data typically means need more model capacity. So it's not surprise by scaling up this model, we can do a lot better than the smaller model or speech-only model and all previous published similar size of the model. Next slide. Next, we also look at the speech classification task. So what we do is we tested for spoken intent classification and also the Flores language ID task. So note that we can see much more different language of text compared to speech in this setup. So that's very interesting to see how this model works on language identification. So our fine-tune pipeline is quite simple. So we just took the output from the MSLAM encoder and do max pooling on top of that, and then feed to a classification layer. Next slide. So we can see for both tasks, it's significantly better than speech-only baseline. For the LangID task, the gain is larger, and it's also benefit more by scaling up the model. Next slide. And now let's look at it back for the ASR task. So can those text data So basically, when we throw in more text data, how it affect the ASR performance. I didn't compare it with language model fusion in this presentation, but you can find all the language model fusion result on the paper if you are interested. So we benchmarked it on 3 different corpus. One is Vox Populi, 14 language, MLS. We use a 10-hour condition. This is 8 language. And the other is Babel, which is from the AirPod challenge. So this more challenge data set compared to others. And we fine-tune it with a 2-layer LSTM RNT transducer. And there's no language model fusion. Next slide. As we can see by this is interesting. Like if we only look at speech only, so if we force the model has same capacity, speech only and speech plus text, there's almost no gains for ASR benchmark. However, like if we scaling up, we can see more improvement. Next slide. So at this stage, our goal was not to improve text modeling. However, like looking, so for example, the whole model is built on conformer, not a transformer. Conformer is particularly good for speech task because it encourages locality information inside the encoder. But it's still interesting to see how well it works for text classification. So we use XNLI as benchmark. It's a cross-lingual natural language inference task, including a couple of different setup. Next slide. So you can see the result was not as good as speech. So for example, if we compare to a small, it's actually not small. If we compare with the state-of-the-art MT5 benchmark, you can see our 600 million parameter model is worse than the similar size text-only model. But the good news is if we scaling up the model, the gap become much smaller. So the conclusion here is it's still like comparable, but it still means like this model needs more capacity to capture both speech and text information. Next slide. So as a summary, so we present a good massive multilingual speech plus text pre-training encoder, and it's particularly good for speech translation task, and it also performs strongly on speech classification, speech recognition, and text classification. As I mentioned in the result section, so if we limited the power, the capacity of the model, it's actually still slightly behind the ASR task. So how can we improve that? Next slide. One most obvious thing is, can we match the 2 modality better? So right now, the modality matching is rely on CDC loss or TLM loss, and also like rely on sharing the same softmax for the mask language model building. However, like it's unknown. Like so one most obvious thing is speech is much longer than text. So how can we like at least make the duration match? Inspired by the parallel tachytron work, basically we use learned duration model to upsample parallel tachytron work. Basically we use learned duration model to upsample the text part and build a TDS system. We actually can do similar things here. That's basically we learn the duration model, and when we train this model for the text part, we first upsample it to make it similar as speech sequence. And then we can use RNT decoder to align both upsample text and the original text. We can also align speech and text. This is going to highly encourage the 2 modalities share in the same space, and it's also a unified framework for speech and text representation learning. Next slide. So this work is more ASR focused. So we compared on 3 standard ASR benchmark. The first one is in US, we use SpeechStew. That's basically 6 or 5 popular in US benchmark, including Switchboard, LibreSpeech, AMI, and etc. And Vox Populi, the multilingual benchmark. And at the end, we will also look at how if it can help speech to text translation. Next. There's a lot of number, but I'll just talk about the conclusion. So basically, it's on par or better than MSLAM across many different domains. And if you look at the paper, we have some evidence. We have some virtualized figure basically showing, in this case, the two modality, the embedding of the two modality actually match better. So that's why it gives better performance. Similar stories for multilingual ASR. Next slide. You can see it improves the previous best result 8.8 to 8.1 by adding text pre-training data. Next slide. And at the end, we also look at if all the benefit we presented before for MSLAM can still transfer to Mastral, especially for this CoVost translation task. As we can see, Mastral is much more parameter efficient than MSLAM. Just building a 600 million model, the result is already pretty close to MSLAM. And if we further adding speech translation and machine translation data to the pre-training task, this shares the same spirit as the JUST framework, which Bo just presented during pre-training stage. It's good also have some supervised signal, and then you do a second stage fine tune. This would match better. So you can see it's actually got a state of the art at that time when we published the paper. Yeah. Next slide. So now we show adding to modality is helpful in some conditions. However, all of those work still require you have a large budget of computes. A smallest model we tried is 600 million parameter. So what if we to do it on a much smaller model, let's say on mobile, the smaller model for production. So this is motivate us to do this JOIST work. The basic motivation is similar, but we want to see how it works on a real product, in a real production setup. Next slide. Just recap, what is the current prod model we use? This is published in last year. It's called Cascade encoder. Basically, you have a causal encoder at the bottom to do the streaming model, and you have more layer on the non-causal encoder that do the second pass correction, and it's gonna output slow but give better accuracy. And the total model size is much smaller. It's a first pass is 50 million parameters, and the second pass is 100 million parameters. Next slide. And by adapt the joint training framework to this semi-streaming model, we actually only do the unsupervised training on the shared encoder part, because it can easily do the mask language model setup. And basically the unsupervised text part only goes through the cascade encoder part. And for the causal one, we keep it as the same. So you can still get an output, streaming output through that encoder. Next slide. For loss computation, it's similar to Mastral. We have we still have the modality matching loss, and we still have the mask language model loss and RMT loss and unsupervised loss. Sorry, it's not similar to Mastral. I mean, it's similar to JUST. This is basically when we train the model, we have both unsupervised loss and supervised loss. Next slide. One big difference compared to Mastral is we want to revisit the text modeling part, because upsample and having actual RMT loss is a little bit complicated for a prod setup. So we can see if we can simplify if we can simplify this part. Next slide. The answer is yes. We don't have to use a learned representation, at least for this setup. So we tried a bunch of parameter-free setup. One is we can do fixed repetitions. So basically, we can repeating subword units by a fixed amount. This is similar to the paper from IBM in 2022, and it's very, very simple, and it works well showing that paper. The disadvantage is it does not model the actual distribution of each word, of each subword unit. So we also try, next slide. We also tried a bunch of variations like random repetition. Next slides. And another way is we can first count the subword and build a Gaussian distribution, and we sample the length based on that distribution. All of those methods is motivated by like, let's try to not rely on a learn duration model. Let's see if this simple approach works in this case. Next slide. Yeah, this is a basically we can also for the pair data we can use false alignment information to obtain the duration model. This is like not train the duration model, but we use false align to get the duration. Next slide. And another benefit for ASR, which we didn't touch before, is so now, so for ASR, we not just do CE training, we also do the MTR training, basically, MWER training. Basically, it try to optimize the expected number of whatever rate. For a standard ASR framework, that's basically you give the hypothesis from, you give speech and you get the hypothesis word, and then you use this MWER loss on top of that. Within JOIST, we actually can compute MWER loss also for the unpaired text representation. You mask it and you get the text sequence, and you can also reuse the information from those unpaired texts. We are also curious about, this is actually similar to how we use machine translation data. That's a big advantage of those like joint representation network. Next slide. So here we train the model on since it's a prod model, it's like we have large amount of pair data for this setup. We are the most interested part we're curious about is can those models improve long tail test set? For example, so we choose like 5 different domain, which is all long tail word, including maps, news, play, and YouTube. Next slide. So you can see here the good news is like even with a fixed representation actually already works pretty well for this setup. We get like a significant improvement among all of those like tail word test set. It's not so for the standard. So we didn't observe gain, also no loss for the like a standard benchmark. I think that is expected because we have large amount of training data. And the real benefit here is because you see this model seeing a lot more text data. So it's actually, it actually improved like those tail word for ENUS. Next slide. Similar trends also hold for pre-train for streaming model, and if we compare it with Mastral, the result is actually comparable. So that means like we can use smaller model budget with a simpler training framework, but we can still get a good performance on those real world test set. Next slide. Lastly, we also looking at how it works for MTR training, MWER training, and you can see like by adding text information, we actually get a more improvement for MWER training. This is basically so if you compare like a standard metric for on those tail word, it gives you something, but not as big as this under this like multimodality pre-train framework. Next slide. Yeah, I think I was just about the time. So a short conclusion is we do believe text injection is useful. We won't claim this is the best way to inject text information so far. Like there's many other way to injecting text information, and there are also other very good paper on this field. But yeah, I think this is I think now it's a time to bring two modality together and let them help each other. And the second bullet point we want to make is we do believe how to matching the two modality are important. And in the future, I think, so now we are mostly focusing on how to bring the modality together for encoder. But you can see clearly a shift on the NLP world. Basically, they are shifting from pre-training encoder to a large pre-trained decoder part. So it's also interesting to see for speech, what is the best framework? Is that a unified framework for both encoder and decoder, or some new proposed approach? Yeah, definitely we want looking for a single efficient model for both speech and text model, and how to also make this model give good performance on text side is also very interesting. Like right now, we can only see comparable for the text corpus. We didn't really see this model improve some standard text benchmark through like speech information. One obvious direction is like for pronunciation learning. I think actually I didn't show it today. It's actually showing some improvement, because when you do pronunciation learning, you do need like speech information and text information. Yeah, I think that's all I have. I think we can have a couple minutes for question that can go for either me, Bo, and Daniel. Yeah, thank you.
Yes, everything was super clear. Not a lot of questions.
Yeah.
I have a question here.
Sure.
Hello, can everyone hear me? I'm Hongyi. My question is, now those text injection model, I think until now, some pair data is still needed to train this kind of text injection model, right? Are there any effort try to remove the need of pair data here? Thank you. This is my question.
So on our side, like we always looking for like a practical setup. So we always assume. So there's this. So for example, in the setup, we have some language we don't have a pair data, but we always assume there's a small amount of, at least like for in US, we always have some pair data to align the two modality. Yeah, I think.
I see.
I think it's a very interesting, like if we remove all the supervised signal, and how can we still maybe one direction is Facebook the zero resource ASR paper, but if I remember correctly, in their setup they still need a lexicon.
Yes, they need a lexicon.
Yeah. This is my personal view, is like for many low resource language, like having a lexicon is even harder than like getting a lexicon is sometimes it's also not easy. So I think if we can do such thing like without any supervised signal, it's gonna be very challenging and also interesting. Yeah.
I see. Thank you very much for the answer. I have a follow-up question. Then in this kind of text injection model, what is the in your point of view, based on your experience, what is the minimum pair data that is required to get this kind of text and speech alignment model work?
We find like we find, so in our setup we find 10 hours good enough, but we didn't like try 1 hour. So I have some experience on TDS. Let's say if the so far what I find is the biggest advantage of having pair data is to make the speech and text easier to like match with each other. And if we take the duration-based model approach, I think it needs about like 1 hour to match the modality. Yeah.
I see. Thank you very much for providing insight. Thank you.
Okay, if no more question, we can take 3 minutes back.
Oh,
Sounds good.
Yeah,
great.
and thank you
Thanks.
everyone to attending the talk. Yeah.
Thanks, everyone.
Thank you.
Bye.
Bye-bye.